Let me move this down a little bit. Let's make a start. Welcome to Earthquakes in Your Backyard. This is EPS 20, which is cross-listed as Letters and Sciences C20Y, I think. And obviously, this is the year to take this class. My name is Richard Allen. I'm a professor of seismology here in the Department of Earth and Planetary Sciences. I'm also the director of the Berkeley Seismological Laboratory. And I can tell you that teaching this class is my favorite part of the year. So I hope that you guys are going to enjoy this as well. The idea behind this class is really to inform the future leaders of our society, yes, that's you, the graduates from UC Berkeley, about the earthquake risk here in California specifically, but also the earthquake risk around the world. Is this too loud? Oh, it's okay? Okay. And so that's the objectives. We're going to talk about the science behind earthquakes. We're going to talk about the impacts of earthquakes. We're going to talk about how we can reduce the impacts of those earthquakes. And we're going to talk about how we engineer buildings so that they are not damaged, or reduce the damage, rather, in earthquakes. And we're going to talk about the individual responsibility that people have to prepare for earthquakes and to take responsibility for themselves, their families, their workplaces, so that the impacts of future earthquakes are minimized on the people that you know, your families, and the people that you work with. So that's the objective of this class. Usually, at the beginning of the class, we talk about who has experienced a serious earthquake. And up until when I taught this last fall, we were talking about the Loma Prieta and the Northridge earthquakes, which were in 1989 and 2004, and there would be a few people in the room who could remember that earthquake and could talk about having experienced it. So how many people in the room experienced Sunday night's earthquake? Wow. How many people did not? Were you not here? How is that possible? Those who didn't experience it? Move-in day. Oh, I see. I thought you all arrived at the end of last week. Well, those of you who didn't move in until Sunday, you really screwed up. Okay? Because if you had arrived before Sunday night, then you would have just felt like the largest magnitude earthquake that we've had here in the Bay Area for 25 years, quarter of a century. Okay, so those of you who did experience the earthquake, tell us what you experienced. Yeah. Noise? What do you mean? All the doors sounded like they were slamming. What else? Rocking, sure. Anybody experience or see any damage? No? Oh, yeah. Your closet broke. Be a little more specific. Okay, and you're saying it with a big grin on your face. Sure, okay. Anything else? Yeah. Wow, the TV fell off. Oh, so it's not attached to the wall. It was standing on the dresser and it fell. Okay. Oh, a big, heavy old. Okay. Anything else? Anybody else? Nobody else see any damage? Okay. So basically just experiencing the shaking but no real damage. Anybody else? Good stories to tell? Anybody in the back half of the room, for example? All the people who experienced damage in the front half of the room? Maybe that's not so surprising. Nothing? No? Okay. So as you can see, this is obviously a large class, but this is going to be an interactive class. It's not just today that I'm going to be asking you lots of questions and expecting you to answer them and give me some feedback. Throughout the class, I want this to be an engaged class where we have some back and forth, and so I encourage you to stop me at any point, stick your hand in the air, and I will come to you and answer the questions that you might have as we move forward. Okay, so let's start on the stuff I have today, but I suspect we won't get through much of it. So the first thing is, those of you who have an iPhone or an iPad, hopefully by now, have downloaded the MyQuake app. How many have downloaded it? How many have not downloaded it? Okay, come on, download it. The MyQuake app is an app that was actually a student project here at the Berkeley Seismo Lab, and it does two things. First of all, it provides real-time earthquake information. So on the app, it shows the last week's worth of earthquakes, and you can go and you can click on the Napa earthquake on your phone, and you'll be able to see what the shaking intensity was here. So when an earthquake occurs, what really matters is not the magnitude of the earthquake. All right? What matters to you is the shaking where you're located. So this was a magnitude 6 earthquake. The strongest shaking intensity, I believe, was 9, if I'm remembering correctly. But here in Berkeley, the shaking intensity was a 5, I think it was. And what we call that light shaking. Okay? So those of you who thought that what you experienced on Sunday night was strong shaking, it was not. That was what we call light shaking. And we call that light shaking because it can get a lot stronger. Okay? So the MyShake app will show you that the shaking intensity here in Berkeley for that earthquake was, actually now I remember, it was a 4, not a 5, I'm sorry. It was an intensity 4, still characterized as, or classified as light shaking. Also, the MyShake app shows you historic earthquakes. So this is what's different about this app compared to any other app that I'm aware of at least, is that it shows you shaking intensity information, not just magnitude information. Okay? We'll talk about that in great deal during the course of the class. Also, we'll talk about the website at the second half of today, but just so you know, this is the website, and the slides from today's lecture, just like they will be for all future lectures, are already posted on there. So if you want to download a PDF of the slides, you can do that right now. Okay, so this is an earthquakes class. We already just talked a little bit about the Napa earthquake, but I'd like to make it a more general question and simply start by asking what earthquakes mean to you. Somebody from the back. Yeah. Sorry? The earth is shifting. Okay, what else? Yeah. The shaking of tectonic plates colliding, that's right. The tectonic plates are scraping past one another, and that's what generates the shaking. What else? Stick your hand up so I can see you. Yeah. A release of pressure. So what it's doing is actually releasing strain, I think is what you mean, but it's releasing strain. So we're going to talk about the very specifics of how the tectonic plates are moving, how that's resulting in an increase of stress on the faults, and how that strain energy is then released, and that's the shaking that you feel. What else? Oh boy, come on, this is the first class. I can stand here a long time. What else do earthquakes mean? Yeah. Oh, really? Did you say many classroom drills? Every, really? I've never heard that before. So is that typical for schools in California? Do you do an earthquake drill regularly? Okay, nobody has ever told me that before. I obviously didn't go to school in California. So every, I don't know, semester or so, I mean, 2 times a year, I don't know, you would do an earthquake drill. So tell me what the earthquake drill would consist of. Okay, that's wrong. I mean, I'm not questioning what you're telling me. It is not true that you should get in a door jamb. There are many myths when it comes to what you should do in earthquakes. And one of them is getting underneath a door jamb. And the reason for that is that the origin of getting under a door jamb comes from the original sort of Adobe-style homes that were built of mud bricks with then a very solid door frame, right? So the strongest part of the building was, in fact, the door frame with a slab of stone or something on top of the door frame. And so getting under that door frame was a good place to be. Today, in case you haven't noticed, the way that they make a door is they cut a hole in the sheetrock. Okay, so being where a door is not a particularly good place to be. What you should do when you experience shaking is duck, cover, and hold on. Hopefully that did come across in there. And what that means is taking cover means getting underneath a sturdy table, something like that. But how would they initiate? How do they tell you, now's the time to do the drill? Okay, and you would do it one classroom at a time or the entire school? The entire school would all do it at 3 o'clock in the afternoon, whatever it might be. Yeah, okay. Ah, interesting. Great. All right, anybody want to add to these drills that you guys do? Anybody done a drill at Berkeley? See one nod. What was the drill at Berkeley? Okay. So was this in October? They had a big shakeout. They call it a shakeout. It's a statewide effort to get people to be earthquake ready. And as I recall, last year they actually announced it on the PA system across campus. So is it possible? Is that what triggered it? Yeah, okay. All right. Okay, what else? What else do earthquakes mean to people? Yeah. Say again? Oh, causing a tsunami. That's right. So, of course, on March the 11th of 2011, there was a magnitude 9 earthquake just offshore of Japan that caused a huge tsunami. I'm sure you all remember the images from that. It's important to recognize that those kinds of earthquakes, they don't just happen in Japan. We're actually expecting a magnitude 9 earthquake offshore of Oregon and Washington here in the US as well. So the same magnitude that could also cause a tsunami just as destructive as the one that struck Japan. Okay, what else? Yeah. Okay. Where did you say you live? Imperial Valley. So I call that the Mexicali earthquake. I know that the seismologist, I believe I'm a seismologist, but seismologists call it something else. I call it the Mexicali earthquake. It was a magnitude 7.1, I think, maybe 7.2, and the epicenter was just south of the California-Mexico border, but obviously it was widely felt across southern California. That's right, that was obviously a very big earthquake, bigger than the one we had in Napa. So that was a 7.2. The one in Napa was a 6.0. The amount of energy released in a 7.0 is 30 times as much as the energy released in a 6.0. So it's a big difference. The Napa earthquake was not a big earthquake. Okay, it's important people recognize that. What else? Yeah. Please tell me that's not true. I know exactly what you're talking about. You're talking about the triangle of life. And this is false information. And so you said that they're making use of that in the public school? This is in California? Wow. So there is this concept out there called the triangle of life. It's fairly straightforward. I hesitate to tell it to you. I'm going to tell it to you, but I want to make sure nobody is under the misconception that this is the wrong thing to do in an earthquake. Okay? And I'll explain why in a moment. The triangle of life is the idea that if there's an earthquake, you should kind of get down next to something. For example, get down next to this chair here. And the concept behind it, which of course makes sense, is that then if the building collapses, the ceiling comes down, that ceiling beams or whatever may fall against this chair, and there's going to be this little triangle of space. Okay? The triangle of life. And this was pushed out a number of years ago, got a huge sort of following, not from people who know about this stuff, but got pushed out on the internet. And it's based on images largely from countries that have very poor building codes, where they show things like buildings that have collapsed. I mean, these horrific images you see where you've had a big earthquake and buildings have pancaked, and there'll be something like a table or a chair or something like this, and there's this little triangular space next to it, and they show those pictures, and that's the triangle of life. It is not appropriate for California. And the reason for that is that most buildings in California are built so that they should not collapse in an earthquake. When you see these big damaging earthquakes in California, we are not so concerned about large building collapse. I mean, we are, but we expect very few buildings to collapse like that. And that's because we do actually have very good building codes. If you are in a modern building, you are in pretty good shape when there's an earthquake. This is a modern building. If you're in an older building, then you have to be concerned. But let's put that to one side. So what you really have to be worried about in an earthquake is not that this building is going to collapse. Instead, the three of you right there need to be very worried about that light that's right there. Okay? It's things like lighting fixtures, ceiling tiles, the kinds of add-ons to buildings, inside buildings, that become dislodged and they fall down. That is what injures people. That is what kills people in earthquakes in California. Okay? So that's the primary concern. So needless to say, getting on the floor here next to this chair is not going to do you much good. Instead, you're much better off getting underneath a table like this. Okay? So the triangle of life is not the thing you should be doing in California. Instead, it's duck, cover, and hold on. Yeah? Right, that's exactly what, and killed 8 people, you said? This is in the Tohoku, the big magnitude 9 earthquake? Yeah, exactly. So that's what you have to be worried about, is this sort of falling ceiling debris, and that's why getting under a sturdy table is the right thing to do. Getting underneath the seats, as difficult as it seems that would be, is the right thing to do in this room. Yeah? Do I know if are modern? I'm not really sure how to answer that question. I can tell you that they've been retrofitted several times. No, so I want to give UC Berkeley credit here. UC Berkeley has spent more than $2 billion retrofitting its campus. A lot of the buildings that were built on this campus, the campus expanded rapidly in the 60s and 70s, which is why we have such elegant architecture across our campus. But UC Berkeley has invested a significant amount of money retrofitting these buildings. Some buildings have been abandoned because it wasn't feasible to retrofit them. Many, many buildings have been retrofitted. There are still some buildings on the list that need to be retrofitted, but the campus is obviously well aware of that. But to UC Berkeley's credit, they have been actively working to retrofit all the buildings on campus. And we'll talk in more detail about that. In fact, we'll talk about all of these things in more detail later, of course. Yeah. So the comment was that she'd heard that the apartment buildings that students often live in off campus are not very safe. One of the key messages that I want you to take away from this class is to understand what a soft story building is. A soft story building is a building that has a one story, typically the ground floor, that is weaker than the stories above. And these are the kinds of buildings that have big openings on the ground floor for garages, things like that. These are the end member cases where you have a wood frame apartment building that's up on stilts, typically again so that you can park underneath the buildings. These are what's called soft story buildings. These are extremely dangerous buildings. And again, this is, unfortunately, these are all built around the time when Berkeley changed its zoning rules. So a lot of the buildings that are typically student accommodation that are sort of around the margins of campus often are soft story buildings. And so you should be able to identify those soft story buildings, and when you're deciding where you want to live next year, you should be factoring that into the equation. Yeah. Does this mean the new bridge passed the test? Oh, that's a good question. So I don't believe there was any damage. It's been a kind of busy week for me, so it's possible stuff has been going on and I haven't seen it. I don't believe there's any damage, so that's good. However, again, this was a magnitude 6 earthquake, and this was up in Napa. So this was 40 kilometers from where we're located right now. And so it's not really a good test, I guess is the point. We have to be ready for a magnitude 7 earthquake on the Hayward Fault. And in case you don't know this, I'm going to have to think, the Hayward Fault is about 300 feet that way. Okay, a magnitude 7. That's 30 times as much energy release as the Napa earthquake. Okay? Silence. Any other comments? How are we doing for time? Any other comments about earthquakes? What earthquakes mean to you? Yeah. Is it true that Evans Hall is the most dangerous building when it comes to an earthquake? Evans Hall is one of the buildings that remains on the list to be retrofitted. Okay, anything else? Yeah. So, okay, we are going to have a disagreement. So first of all, make sure I understood what you were saying. So you were close to the location of the Sichuan earthquake in 2008? Okay, and so again, tell me what happened, what you think happened before? So what migration? Okay. So tell me exactly what you saw and exactly when you saw it. And when was this? When? Oh. Okay, so 12 hours before kind of thing. Yeah. So in case you can't hear, the report that we're hearing is that prior to the Sichuan earthquake, and I forget the magnitude, about a magnitude 8 in China in 2008, the report here is that there were frogs that were moving across the road and barking dogs about 12 hours before the earthquake. In fact, similar, it may well have been the same observation, but a similar kind of observation was reported in the news media as well. I can tell you that every time I give a public talk about earthquakes, I get asked the question, can animals predict earthquakes? And I can tell you the answer is no. Okay? There are many reports in the media, like this, of animals exhibiting unusual behavior prior to earthquakes. The problem is that what people do not report in the media is all of the times when animals are not exhibiting unusual behavior. So if you take any particular noon on any particular day and you look for some animals exhibiting unusual behavior, you're going to find some. Okay? So the point is that there is no consistent evidence of animals exhibiting unusual behavior prior to an earthquake. All there is observations like the one you're describing, which of course are after the fact. Oh, we just had this big earthquake and I saw these animals doing unusual things. Animals cannot predict earthquakes. Scientists cannot predict earthquakes. There is no way that we can predict earthquakes, and we do not think that we will be able to predict earthquakes for the foreseeable future. Okay? That's another key message that I want you to take away from the class. Okay? All right, anything else? That was a good comment. I'm glad I waited for that one. Anything else? Yeah. On some what, sorry? Right. You're my favorite student. The comment here, what's your name? Write that down. Yeah. So Gabriel here is reflecting on, did you see this or you just saw the reports? Okay, YouTube, of course. 30 seconds prior to the magnitude 9 earthquake in Japan, that on the TV screens, some kind of alert popped up, is what you're saying, right? And that's, in fact, that is correct. That is not an earthquake prediction. That's what we call earthquake early warning, okay? Because what's happening there is that we are detecting the beginnings of the earthquake, very rapidly assessing how big that earthquake's going to be and pushing out a warning, okay? So, okay, so I did like you. So the comment was, couldn't this explain some of the misconceptions of the animal? And the truth is that you're actually exactly right. There was a magnitude, I forget what it was, but like a 7 or something in Eureka, northernmost California, a number of years ago, and there was a video that was put out by the media widely, and it was a video camera, like a security camera in an office building. And yes, okay, this guy's watched them all. Okay, so it's an office recording in an office, and what happens is you see suddenly there's a dog, a lab, sat in the corner, and suddenly the dog jumps up. Clearly something has startled the dog, and the dog runs off, and then, I forget what it is, like 10 seconds later or something, you start to see the shaking. And so this was put out widely. CNN, I remember, was talking about it for hours, and talking about dogs predicting earthquakes. And in fact, when you actually look at where the video comes from, the difference between the time between when you see the dog react and when you see the shaking in the video is the difference in time between when the P wave arrives at the building and when the S wave arrives at the building. These are two types of energy that are both radiating from the earthquake source, and we will talk about P waves and S waves. And so the dog is just more sensitive and felt the P wave and reacted. The people didn't feel the S wave, but they did feel, didn't feel the P wave, but they did feel the S wave. So that's correct. So that is part of the misconception, but the 12 hours, of course, this particular observation, 12 hours, it doesn't explain it. But back to the early warning, which is when you became my favorite student. Earthquake early warning is something that we actually have been working on very hard here in California as well. The system in Japan, they turned on their public earthquake early warning system in 2007, and this 2011 magnitude 9 earthquake was the first true test of that event, and indeed they detected the earthquake and they pushed out a warning. And in Tokyo, for example, I think they had about a minute and a half worth of warning. So that was a huge success for the seismology community in the sense that the researchers, people like me, who have been working on developing this system, an earthquake happens and they pushed out a warning. So, good segue into, I'm going to show you instead the next slide. For the Napa earthquake, on Sunday morning, in fact, was a great demonstration of we call it a demonstration earthquake early warning system that we have developed here for California. We're running here at UC Berkeley, and this warning system detected the earthquake, and this is the warning that was received here at the Berkeley Seismo Lab.
Earthquake, earthquake.
Okay, that's not much warning. That's 5 seconds of warning, okay? So nobody wants it? You're all laughing. So does this mean nobody wants it? So you wonder, well, what use is 5 seconds worth of warning? The amount of warning could be anything from a few seconds to a few tens of seconds. The best case scenario for a warning in California is about a minute's worth of warning, okay? And so what this is an app that we have